Swayam Prabha. Digital India. Educated India.
So, welcome to today's class, and we were talking about the role of external mass transfer resistance in the context of a catalyst in the last class, okay. And when we spoke about the cooling of a sphere, also we spoke about heat loss through Newton's law of cooling, where again you had this concept of heat transfer coefficient, okay. So, what I want to do is go a little bit back and talk about how these heat transfer coefficients are calculated, estimated, how do you get these dimensionless heat transfer coefficients, Nusselt number, okay. And these are things you are kind of familiar with, but there is scientific basis behind doing this, and I want to basically illustrate the power of making things dimensionless, okay. So, dimensionless analysis helps you get some information, and basically that is what we want to see, how we can use dimensionless analysis for analyzing behavior in a very precise, concise way, okay. So, role of dimensionless analysis in analyzing heat and mass transfer problems, okay. So, we will first talk about heat transfer and then kind of complete that, then we will talk about mass transfer, okay. I do not want to keep shifting between heat and mass, and the idea is there are similarities and there are dissimilarities. So, that is what I want to emphasize on, okay. So, most of the time we say if you have done the analysis for heat transfer in a particular way, you should be able to do the same thing for mass transfer, but there is a difference, okay, and that is what I want to emphasize. So, let us focus on heat transfer. So, you have some body, okay, some arbitrary shape, and there is a solid body here, and for the sake of keeping this discussion very focused, we will assume that the temperature everywhere on the body is T0, okay. The temperature here is T0, and there is liquid or gas or fluid flowing past it, and what you are controlling is the temperature far away, which is T infinity, okay. T infinity is the temperature far away, and you have this body, you are having the liquid flow, and again to keep things precise, let us assume T0 is more than T infinity. So, what will happen is there is going to be heat loss from T0 to from the solid body to the colder liquid, okay. So, T infinity is far away temperature, T0 is more than T infinity. So, body loses heat, to the fluid, okay. So, you want to basically find out, I mean things like what is the temperature profile, what is the velocity field, what is the temperature field, and what is the rate of heat loss. Those are the kind of typical questions which is of interest to you, okay. So, we want to find U, temperature and heat loss rate. Okay. So, I need all of these are coupled. So, when it comes to finding the velocity field, what we have done so far is we have always assumed that the properties are all constant. Okay. And because we never worried about the viscosity is a function of temperature, except when we were doing this problem on the natural convection, then we worried about density as a function of temperature. Okay. But when you have heat transfer, clearly there is going to be a temperature profile. Okay. Temperature is not uniform everywhere in the fluid. So, temperature is going to change. So, if temperature is going to change, then the physical properties, density, viscosity, specific heat, thermal conductivity, all of these are functions of temperature, and the question is, do you want to include that in your calculation? Okay. So, basically in heat transfer problems, here properties are all functions of temperature. For example, mu, rho, Cp, K, whatever. Okay. And when you supposing you are interested in analyzing the problem of natural convection, then you have to necessarily include the effect of density dependency on temperature. Okay. Because natural convection is when you have higher temperature at the bottom, lower temperature at the top. Higher temperature means density is low, and so this liquid will have a tendency to rise up, the fluid will have a tendency to rise up. Okay. So, if you are interested in your particular system to analyze the effect of natural convection, then I have to necessarily include rho as a function of temperature. Okay. I can possibly treat the other properties as constant. Okay. So, if we want to analyze natural convection, then we include rho as a function of temperature, because if you do not include, if you treat rho as a constant, then there is no question of any buoyancy, there is no question of any lesser liquid, dense liquid rising up. Okay. So, what is the physical problem you are trying to analyze, that is going to tell you what kind of assumptions you have to make. Okay. And we can treat others properties as constant. Okay. That is what you can see. But so, but in typical forced convection systems, where you say, look, I am pumping liquid at a particular flow is much higher, it is dominating the effect of natural convection, I can neglect the effect of natural convection. Then you need to, you can make the assumption possibly of all the properties being constant. Okay. So, here where the natural convection effect is low, we can treat all properties as constant. Okay. So, that is something which you have to keep in mind. Of course, whether this treating all properties as constant is a valid assumption or not, only after you do all the calculations and do the analysis you will be able to say if it was valid. Okay. But to begin with, maybe you can assume. So, this is typically what is done. So, although you have temperature variation, of course, the temperature variations are very significant, then you may want to include the effect of the property variation, or if the temperature variation, let us say going from let us say 300 to 500 Kelvin, then you may want to just say I will take the average property at 400 Kelvin and do the analysis. Okay. So, because 400 is a representative average, or in that particular range 300 to 500 Kelvin, which is what you are observing experimentally, okay, and you want to do the analysis, you want to see how much is the change. Is the density change 1%, 5%, 10%? So, if it is changing significantly, then you may want to include. So, that is the call you have to take. Okay. And then you go about doing the modeling. So, you need to it is not that we are doing something arbitrary, you can decide on the you can do a thoughtful analysis. Okay, how much is the viscosity change in the temperature range of interest to you. If it is not significant, then you say I will assume constant and go, or take an average value and go. Okay. So, this is typically what is done. So, although we are dealing with a heat transfer problem where the temperature is changing, we will normally assume the properties are constant. What is the advantage of this? The advantage of this is mathematically we are decoupling the momentum equation, the Navier-Stokes equation, the continuity equation from the energy equation. When I assume the properties are constant, I can solve for the velocity flow field, and then I can use that velocity flow field in my energy balance equation. Otherwise, I have to solve for the momentum equation and the energy equation all together simultaneously, because because in the momentum equation I have density, I have viscosity, that is a function of temperature, energy equation has temperature. So, everything has to be solved together. Okay. So, basically this assumption decouples the velocity field from the temperature field. It is a one way coupling. The velocity field affects the temperature does not affect the velocity by making this assumption. Okay. So, what I mean by that is we solve for u and then find t. U affects t, t does not affect the velocity. Okay. So, it is a one way dependency. So, if I were to write the governing equations, what I would do is I would write let us say, let us assume my liquid is incompressible, okay, just to keep life simple. Divergence of u equal to 0, this is my continuity equation, and this is a vectorial, this is all vectorial. Okay. Rho du by dt plus u dot del u equals minus gradient of p plus mu del squared u. Okay. The gravity term I am absorbing it in my pressure like I discussed before. So, I am not considering the gravity term explicitly, because this pressure is considering my effect of gravity. Okay. So, this includes the effect of G as discussed before. So, now what I want to do is I want to make this equation dimensionless, and when you want to make an equation dimensionless, you realize that you have to choose characteristic scales, okay. And again, to make my life simple, maybe I will just look at the steady state problem. You do not have to do the steady state problem because I can choose the t characteristic properly, but let us also assume steady state, although not necessary. So, u characteristic will be, let us say, u infinity far away, okay. And then what else do you have? Length scale, L characteristic is, let us say, some L, some length scale. If a sphere is the radius of the sphere, okay, whatever the body is, if it is some other body, look at the characteristic shape. Point is, I am using the same length scale for both x and y directions, okay. And so for all the variables I am using the same length scale. I am not using different length scales for different directions, like sometimes we did when we were doing the lubrication approximation, okay. So now if I want to do that, then this first equation will get simplified to del star dotted u star equal to 0. What have I done? I have taken out a u characteristic, and here I will get an L characteristic out, because x and y, supposing I am working in Cartesian coordinates, okay, then both x and y I am scaling with L. So, one L will come out. So, and then this cannot be 0, therefore, I say del star dotted u star equals 0. I want to make the momentum equations dimensionless. Again, since I made it, so what am I going to get? Rho comes here, this u is going to give me one u characteristic, the del is going to give me L at the bottom, okay, and this u will give me another u characteristic. So, I get another u characteristic times u star dotted del star u star, okay. So, I made it dimensionless. If you choose t characteristic as L by u, suppose you choose t characteristic as L by u, you can again convert this to du star by dt star, and again you will get the same thing, okay. So, steady state and unsteady state really does not matter, but let us just do this, minus p, I am converting this to p star. So, I will get a p characteristic out, I convert this to del star, so I get an L out, okay, plus mu del squared u, so I get an L squared out times the u characteristic out del star squared u star, okay. So, what I am going to do is I am going to divide everywhere by L square by mu u c h. So, or multiply by L square by multiply by L squared by mu u c h. Then I would get mu h by L times L squared by mu u c h okay, and this is your Reynolds number times u star dot del star u star, and if I choose my PCH such that this coefficient becomes 1, because PCH I have not defined yet. So, I can choose my PCH such that this coefficient becomes 1, I get minus del star squared P star plus del star squared U star for PCH equal to mu UCH divided by L. Okay. So, basically what I am trying to make here is, it will appear to you that the velocity is a function only of the Reynolds number. Okay. So, velocity is U star a function of Reynolds only, because I mean of course space is there, space and that you have made it dimensionless, but what is the parameter it depends upon? Only Reynolds number and x star of course. Okay. I can't say this for sure, because when I am solving my differential equation I need to look at the boundary conditions as well. I have to make sure my boundary conditions do not have any additional dimensionless parameters. If my boundary conditions have dimensionless parameters, then my U star will depend upon those parameters also. Okay. So, I have to check my boundary conditions to decide. So, basically are the boundary conditions independent of dimensionless parameters. So, in this case the boundary conditions are going to be far away as x star goes to infinity, velocity is u infinity, that is what we said, velocity was u infinity. So, u star will be 1, u star is u divided by u infinity, okay. U star is 1, and on the sphere, on the body, because of no slip, no penetration condition, u star is 0. So, basically point is the boundary conditions I am not getting any additional dimensionless numbers. Yeah. Yeah. We do not consider pressure term here. Pressure term will come into the picture if you for example have a free surface or something, then and if your gas, if a fluid is let us say a gas, then the pressure effects will be dominant. Okay. If you are looking at liquids, then you do not need to worry about the pressure terms, because the velocity is going to be decided by this thing. So, basically you will convert this to equations which will have only the velocity field, and then you can solve like we did before. You can eliminate the pressure if it is a 2-dimensional flow, and then you can solve. Okay. So, what I am doing is I am specifying the velocity, and that is enough for me to solve the problem. Okay. So, yeah. So, now so because the boundary conditions are independent of any dimensionless parameters, u star is a function only of Reynolds number and x star. Okay, because I am looking at steady state. Now, what about temperature? For temperature, I have to look at again temperature is given by this energy equation. So, this is what I was telling you. This is what, that I can solve for the u star explicitly, because I have assumed my properties are constant. If my properties are not constant, this viscosity, density, all of this will depend on temperature, and I have to solve this along with my temperature equation. Okay. So, I can now solve for the velocity field, and then I look at the energy equation at steady state, and that basically tells me rho Cp times u dot del T equals k del square T. I have neglected any generation of energy like reaction or viscous dissipation for now. Okay. So, if you have to include those. Okay. No neglecting source and viscous terms. So, again I want to make this dimensionless. The other thing is I want to make it dimensionless this also, and I am going to use the same length scales, but for velocity and length I have already decided. But what about temperature? Temperature I am yet to decide. So, temperature I am going to make it theta as T minus T naught divided by T naught minus T infinity. I should make it T, I think I should make it T minus T infinity, no? Yeah. Yeah. T minus T infinity divided by this. So, what does this mean? At x star equal to infinity, theta will be temperature is T infinity, theta is going to be 0, and on the body theta will be equal to 1 because temperature is equal to T naught. So, basically when I solve this energy equation I will have boundary conditions, okay, and the boundary conditions are not giving me any new parameters, okay, by when I choose it like this. So, it is only 1 and 0 just like my velocity, but let me see if any new parameters are coming in my energy equation, okay. So, I have again make it dimensionless, rho Cp u characteristic, okay, when L will come out, and temperature when I make it dimensionless I will get the scale, gradient of temperature will be T naught minus T infinity times gradient of theta. Can you see that gradient of theta is equal to gradient of T multiplied by T naught minus T infinity. Gradient is just, let us say, d by dx or d by dy, okay. So, you can see that. So, now I get an L, I am going to make the length scale also dimensionless, and I will T to convert to theta I get T naught minus T infinity times u star dotted with del star theta, okay, and then this is k times L squared times T naught minus T infinity times del star squared theta, okay. So, I have just made this dimensionless, and now I am going to move these guys. So, T naught minus T infinity cancels on both sides. I have rho Cp u Ch by L multiplied by L divided by K times u star dotted del square theta equals del star squared theta, okay. This is what I am getting. So, I can write this is a dimensionless group now, which contains some of the thermal parameters, specific heat and thermal conductivity and all that. And this group is called Peclet number. So, Peclet number is L UCH divided by alpha. Alpha is the thermal diffusivity, K by rho Cp, okay, where alpha is K divided by rho Cp. So, now the temperature would depend upon Peclet number, velocity depends upon Reynolds number, okay. So, basically what I am saying is theta is going to be a function of Reynolds number times Peclet number and x star, because in steady state it does not depend upon time. So, as far as velocity is concerned, it depends only on Reynolds number, but as far as temperature is concerned, it depends upon Peclet number. And this particular Peclet number, I am going to put a small subscript h here to tell you it is Peclet number associated with heat transfer, okay, because it has thermal diffusivity. Associated with heat transfer. And what I can also do is rewrite Peclet number as Reynolds number multiplied by Prandtl number, where Prandtl number is nu divided by alpha, ratio of the what diffusivity is it? The kinematic viscosity and the this thing, kinematic viscosity and the thermal diffusivity, okay. So, many people would like to write, what is that, how do you choose? So, theta now will be a function of Re times Prandtl number times and x star. So, when you are analyzing a particular system, the one thing which you can do is you can look at fixed body, fixed fluid, and experimentally if you want to study the effect of heat transfer, what you would like to do is you would like to vary the velocity, okay. You would like to vary the velocity with which the liquid is flowing far upstream. U infinity is what you can control. You have the body, you are pumping liquid at the high velocity, body is fixed, the geometry is fixed, everything is fixed, okay, and T infinity and T 0 do not show up in the equations because the way you have scaled it. The only thing which is in your control is U. So, you want to vary U and study the behavior of the system. What happens? U is in both Reynolds number and Peclet number. So, experimentally if you do studies and you want to show your results, okay, when you want to show your results, you want to study the effect of one parameter at a time. So, experimentally you vary U, you are changing both Reynolds number and Prandtl number, but if you change U and you write everything in terms of Reynolds number and Peclet number, you change both. If you write in terms of Reynolds number and Prandtl number is independent of U. So, only Reynolds number is being changed, okay. So, people like to prefer using this, yeah, Reynolds number and Prandtl number for their notation. So, basically Peclet is Reynolds multiplied by Prandtl. This is preferred because you can study the effect of one parameter at a time, okay. So, Prandtl number is independent of U infinity. So, it is while varying U infinity, only Re changes, okay, and Prandtl number is fixed because it depends only on the fluid properties nu and alpha, okay. For a particular fluid you can just keep changing your velocity and all the effect is captured in Reynolds number. So, then you can make a plot, you can plot whatever you want to plot, you can plot as a function of Reynolds number versus something whatever unknown for fixed Prandtl number. I mean, that's how you like to depict your results. But if Prandtl number, but if you do the other way, if we write theta as a function of Reynolds number and Peclet number, when you vary Reynolds number, let us say by varying velocity, Peclet number also changes. So, in the graph, two things are changing. Okay. So, you do not know whether it is a change in the Peclet number which is causing the problem, or whether the change in the Reynolds number is causing the problem. Okay. So, here Peclet number changes. So, what is causing the effect observed? We can answer that. Okay. So, basically, so you will see that the temperature depends upon, so people like to work with Reynolds number and Prandtl number. So, now, so theta depends upon Reynolds number, Prandtl number and x star, and if you look at heat flux, okay, if you look at, you want to look at the heat flux, that what is the heat loss, that is what we are interested in finding out, what is the rate at which heat is being lost from the surface. So, if you have some fin or something, you want to make sure the temperature does not heat up too much, good heat transfer is there. How do you calculate the heat transfer? Q, the rate of heat loss the surface is given by minus K n dot del T integrated, this is the K of the fluid, okay, integrated over the surface dA. So, this body has a area A, okay, and at every point the temperature is constant, but the gradient can be changing, the n normal direction can change, okay, because it can be arbitrary shape. So, I am just saying K n dot del T dA is the rate of heat transfer from the n is the direction of outward normal, and n is outward normal. Okay. This is the rate of heat transfer that you have. Okay. You take a small area element, it is n dot K n dot del T dA, I am integrating over the entire surface, the surface integral. So, the double integral. Now, what people like to do is they like to write everything in terms of dimensionless numbers. Okay. So, basically the Nusselt number is the dimensionless heat transfer coefficient, okay, and this is a measure of the rate of convective heat transfer to the rate of conductive heat transfer. Okay. So, this is basically is rate of convective heat transfer to rate of conductive heat transfer. Okay. And the way this is defined is a factor of 2 is added, 2Q. So, you basically what it means is, in the presence of the flow field, I have to calculate what my temperature solution is, theta or temperature, and then find the gradient, and then I have this thing 2Q, and then I have surface area multiplied by K fluid C infinity divided by L. Okay. So, this is the way the Nusselt number is defined. The denominator tells me the rate of heat transfer only by conduction, So, that is the temperature difference is T naught and T naught on the surface and T infinity far away, and suppose there is only conduction between these 2 points, it will be K times this divided by L, okay. And I have multiplied by the surface area, you can calculate it, 4 pi r squared for sphere, for whatever it is for the other body. So, this is a representation of the rate of heat transfer by conduction. How do you calculate this? This you calculate by looking at the numerator Q, because you have to solve that energy equation, U star dot delta theta star equal to del square theta star multiplied by Reynolds number and Prandtl. You find the temperature solution, okay, and once you find the solution for the theta and temperature, you will substitute it here, because now that solution includes the effect of convection. The solution which you get by solving the energy equation, so this includes the effect of U, the convection, because I am solving the energy equation to get that temperature, okay. So, the numerator has the convective effect, the denominator has only the conductive effect, okay, and that is what I get. So, clearly Q depends only on these guys, and if you were to convert it to dimensionless form, you will see that this depends only on Reynolds number and Prandtl number, okay. So, point I am trying to make here is Nusselt number is a function only of Reynolds number and Prandtl number. I mean, that is the reason you write your correlations as a function of Reynolds number and Prandtl number, okay. You I mean, and how do you exactly get that correlation? There are a couple of ways. I mean, people do experiments for different Reynolds numbers, different Prandtl numbers, and calculate the Nusselt number, and then they fit some kind of an expression, some equation, and then you get your correlation, okay. That is how you get the correlation for Nusselt number. I just wanted to convert this, last thing I want to do is convert this to some dimensionless form, because I found the solution in terms of theta, not in terms of t, and I will leave the rest of the stuff to you. So, I just wanted to tell you that there is a, so dimensionless analysis is what has helped us get the dependency of Nusselt number on Reynolds number and Prandtl number, okay. And yeah, of course, we made a bunch of assumptions. So, how do I convert this Q to minus K integral n dot del T dA over the surface? If I want to convert this, write it in terms, what am I trying to do? I am trying to write everything in terms of my dimensionless variables now, okay. So, when I make it dimensionless, this T will give me a T naught minus T infinity, and del will give me an L at the bottom, because that is my length scale, okay. So, this will be, let us say, n star, the unit vector anyway, delta del star theta, and have minus K, one L comes at the bottom, and one T naught minus T infinity comes at the top, okay. T has been made dimensionless with theta, del I get L, and our dA star, this also has length scale, 2 length scales. I am making it dimensionless. So, when I make it dimensionless, I will get an L square as the numerator, because I have converted dA to dA star, okay. So, this is basically minus K into T naught minus T infinity divided by L times integral n star del star theta dA star, and I want to get rid of this L here, I put an L here. That is your numerator in terms of the dimensionless temperature theta, that is your numerator, okay, that is heat flux. So, you have to evaluate this. The idea is, why am I putting an integral? Because the gradient can change from point to point on the surface. The gradient does not have to be equal. If it is equal, then it will come out of the integral and just multiply it by area. So, if it is a sphere at a uniform temperature, everything is symmetric, then it will be area multiplied by dt dr. Okay. So, that is the whole point. So, this allows for change in the gradient along the surface. If the gradient changes at different points, you will have different gradients, different rates of heat transfer. So, right now what I have done is I have just assumed properties as constant. If you were to see, there are, depending upon the problem, if you have a natural convection situation, then you say the Grashof number becomes important. Okay. So, how do you get that into account? Then you have to include density as a function of temperature in your governing equation, because natural convection means density is a function of temperature. Then you make the equation dimensionless, and then one more variable will come into the picture, one more dimensionless number will come into the picture, and now your correlations will be in terms of that dimensionless number. So, and when you choose your dimensionless numbers, you choose it in such a way that if you are trying to study experimentally the effect of one variable, like maybe velocity or temperature, you have to make sure that particular variable only affects one of the dimensionless numbers. If you change one variable, if it is changing all the dimensionless numbers, then you really do not know which effect is dominant. Okay. So, those are a couple of things you have to keep in mind, and why you choose Prandtl number and not Peclet number, because of that reason. Okay. Okay. So, what I will do is next class we will look at the mass transfer problem. Mass transfer, it will appear is very similar, but it is not. So, some subtle differences are there, and we will look at what those differences are, okay, when you have a mass transfer problem. So, although properties you will keep as constant, there will be a contribution to the velocity field, okay, not because of natural convection. So, that is what we want to see. So, mass transfer is slightly different from heat transfer. So, here we said no natural convection and we proceeded, but in mass transfer you will see it is not the case.